There you go.
Bobby, you want to carry? I'm still trying to decide what part of what aspects of renormalization to go through, and so I'm going to start today by talking about a couple of different things. One is a little more about the Landau-Ginzburg traits. And then I'm going to go through something that I mentioned last semester but didn't actually show you in class. It's I think it's quite an important paper of Glauber's a long time ago, in which he showed what quantum state is radiated by a classical current. And in fact, I think an appropriate, a good treatment of Bremsstrahlung should actually be based on, should make use of at least that result. So I'm going to go through that. And then I'll start doing either the vertex correction or the vacuum polarization. I'm not quite sure which one to do today. The treatments are all somewhat different. So let me first remind you that Landau and Ginzburg used a Gibbs potential, and it was this. So this is the magnetization, and this is the external field. And this is written and assumed to be of the form A plus B of 2 m squared plus c of 2 m to the 4th minus hm. And what we saw last time was in particular that m was approximately Tc minus T. Well, in general, it's Tc minus T to the beta, where beta is the critical exponent, which depends upon what class of substances one is talking about. But last time we were talking about basically a ferromagnet. And let me clear up one item, one point that occurred to me as I was lecturing, and I didn't quite know how to explain it to you. We arrived at this formula for the spin correlate, for the response of the spin density to a delta function spin density at the origin, and what we got was e to the I k dot x divided by k vector squared plus 2b, and we got t minus tc, and I was worried, well, what about t less than tc? Well, the point is this whole analysis is for t greater than tc. So the idea is that you have this critical point here at tc, you have the magnetization here, and this is the temperature axis, and you're coming down in temperature. You have a second order phase transition there, first order here, and you're looking at this for t greater than tc. That's why we didn't need to consider the case where this was negative and there'd be a singularity. Okay, let me now just go to another variable, namely the susceptibility. And the susceptibility chi is partial of the magnetization with respect to the external field, and it's at the external field set equal to 0. And so what we do is we first take one derivative of this, the derivative with respect to t, and what we get is, actually, let me see, I'm just a little puzzled as to why. Oh, that's right, we want to minimize this. So first we minimize this and we get the equation 0 is minus h, that's from this on the other side, and this is partial g, partial m, and that's 2b m plus 4c m cubed. So that's taking the derivative of that of the Higgs potential of the Gibbs potential with respect to m. And now, if we take a derivative of this with respect to h, what we get is minus 1 is equal to 2b, and this is partial of m with respect to h, and that's chi, and then this is 4 times 3c m squared, and then another derivative chi. And so this gives us a formula that chi is equal to minus 1 over 2b plus 12c m squared. And now, if we use the previous result that m squared is is b over 2c tc minus t, and we've set b equal to b t minus tc, then what we find is that chi is minus 1 over 2b t minus tc plus 6b tc minus t, and this is altogether 1 over 4b t minus tc. And I think we're supposed to be in the region of t greater than tc here. And so what do we have here? Here what we have is that this is going as t minus tc to the minus 1. So the critical exponent in this case is minus 1. And in fact, the critical exponent is gamma, and so this is equal to minus 1 for this, this case. I think it would be fun to work out some more examples of this, but I don't really know where such things are done. I found some things on the web, but you may know of better sources. If so, send me a link. Okay, I think I'm now going to do this paper of Glauber's that was that's quite old, but I think it's been ignored by. I mean, the people in the quantum optics community know about it, but the people outside of the quantum optics community, I don't think do. And that's sort of too bad. So let me first say what this, what I'm going to use to do the calculation. And this is something called Glauber's identity, and I think I mentioned this last semester. This is equal to e to the a plus b plus a half commutator of a with b, and this is for the case if a commutes with the commutator of a and b, and if b commutes with the commutator of a and b. So this is an identity that holds in these cases. Now, I don't think I proved this in class last semester. You guys may have seen it in class when you took quantum mechanics or something else.
I don't remember seeing it proved. I remember
this identity.
I don't remember if I saw the proof, but I know I've seen it.
All right. Well, why don't I go through the proof, because I think it's very important in quantum optics. It's very important, and in other things, it's I think in the case, I think it's the basis of Glauber's paper in which he showed that a C number current coupled to a quantized electromagnetic field produces a coherent state, or maps the vacuum into a coherent state of the radiation field. And so let me go through this proof then. And what I'm going to do then is define A sub b. And unfortunately, in my notation here, I chose t as an auxiliary variable. You're not to think of this as time, despite the fact that it looks like time. But I don't think it would be good for me to switch to lambda or something on the fly, because I'd probably screw up at some point. So let's define this as e to the minus tb, a e to the tb. And the t derivative of this, and I suppose the reason I did that was that I could write dot instead of backslash fraction and then squiggle, squiggle, and so forth. So what is this? Well, this pops down a minus e to the minus tb b a e to the tb, and then plus e to the minus tb a b e to the tb. And so this is e to the minus tb, the commutator of a with b, e to the tb. And on the other hand, we've assumed here that the commutator of a with b commutes with both a and b, in particular with b, and so we can move this exponential through, in which case it cancels that one. And so this is just equal to the commutator of a with b. And we also know that a sub b of 0, of course, is just a, because if you set t equal to 0, you just get a. So what is a sub b of t? Well, it's going to be a sub b of 0 plus an integral dt of a sub b dot of t from 0 to t. And so this is equal to a plus an integral 0 to t dt of just ab And that's just equal to A plus AB times T. So these,
Sorry, I have a question. Do we have to make some assumptions about the like e to the TB, e to the minus TB being irreducibly represented that way for that to for you to write that last step there, that commutation to be true for the two exponents to cancel, like that to just.
okay, so which step are you worried about?
The very end there.
This to here?
Yeah. Is there some additional assumptions that have to be made for that?
Well, we
About-
assume that the commutator commutes with B.
Right. I obviously.
So you can certainly move this through,
So there.
and then you've got e to the
restrictions are-
minus TB times e to the TB.
Okay. I'm just trying to make sure I understand exactly what those.
Well, of course, you know, we are north of Lomas. And so that means that we are in a mathematician-free environment. I imagine there are all kinds of things that one could say.
I think all we did on this before was you just expand e to the TB in the Taylor series.
No, that's how you get.
Actually, you know, that's what that, by the way, that's what people say in textbooks, and that's what everybody says. But it's actually not the right thing to say. The right thing to say is that B is an operator that you can expand typically in terms of its eigenvalues and eigenvectors, and then you can define this thing in terms of the eigenvectors of A and of B. That's a better way of thinking than thinking in terms of an infinite series.
Yeah, I think.
Because it works when B is Hermitian, but also if B is unitary, it has eigenvalues and so on and so forth. So there's a whole class of, in fact, basically if a square matrix is not defective, which is a lovely mathematical term, it allows you to just ignore anything you don't like. Anyway, a matrix that's non-defective can be expressed in terms of its eigenvalues. And, but in any case, as I said, we're free of, we're in a mathematician-free environment. Although when we move to the new building, that won't be so clear anymore. Okay, so that's A sub B. Now let's consider this. E to the TB, AB of T, is what is that? That would be e to the TB A plus e to the TB AB times T, and also notice that what did I do? So this is A. Let me just rewrite this. So in particular, B, I don't know why I'm going to say that. Never mind what I was about to say. Let me go back to this definition, by the way. There's the definition. So by the definition, e to the TB times a sub b of t, you see these factors cancel, so this is automatically e to the TB. And so what we have is that this is a e to the TB. So we have this equation, which is what I want to work with in a moment. So now we're going to define something else. G of t as e to the TA, e to the TB, e to the minus T A plus B. And now compute G dot of T. And if you do that, then what you get is e to the TA, A, e to the TB, plus e to the TB, B, minus e to the TB, A plus B, e to the minus T, A plus B. And now we can rewrite this as e to the TA. Bring this term forward, we get e to the TB times B. And then here we have yes, okay, so here, in order to, so I brought this term forward, this term, A, e to the TB, this is equal to these things, so I'm going to put them in there, and so that is plus e to the TB, A, plus e to the TB, AB times T, and then we have minus e to the TB, A plus B, e to the minus T, A plus B. There must be a neater proof of this. I think this proof is shorter than the one in Mandel, but okay. So what do we have now? Let me make sure I've got the same thing as in my notes. Yeah, all right, this is exactly the same. Okay, now we've got some cancellations occurring, although it's not. Okay, here e to the TBB cancels this one, e to the TBA cancels that one. So this really does collapse. This is just e to the TA and e to the TB. So everything is canceled except this commutator term, and then e to the minus T, A plus B. Right. On the other hand, that, since the commutator commutes with both A and B, we can rewrite this as T commutator of A with B times this, times that, but that's just the definition of G of T. And on the other hand, G of T is constructed out of A and B, and G of T, therefore, commutes with the commutator. So we can also write this as T, G of T, AB. So those are two different ways of writing it. So that means we have an equation here, G dot is equal to G times another matrix, but it's a matrix with which it commutes. And so we can rewrite that as ddt of log G, which would then be G dot over G, and this is equal then to T times the commutator of A with B. Now, if we integrate this, we get integral 0 to 1 ddt log G dt is log G of 1 minus log G of 0. This is then equal to the integral of that, but that's just the commutator of A with B. And so what does that say? Well, G of 1 is e to the A, e to the B, e to the minus T, A plus B. So we can write that as G of 1 minus let's see, what is G of 0? G of 0 is just 1, and the log of G of 0 is just 0. So keeping these as logs, so the log of G of 0 is 1, so the log of G of 0 is just 0. So this is log G of 1 is the commutator of A with B, and so G of 1 is e to the AB, e to the commutator. But this is the result we were trying to prove, namely that this is e to the TA, e to the TB, e to the minus, well, we're talking G of 1, so this is e to the A, e to the B, minus the commutator of AB. And now I've got log G of 1 oh, sorry about that. We're integrating this with respect to time. The integral of t is t squared over 2. Evaluated between 1 and 0 is a half. So this is a half. And so we have G of 1 is a half there. And so this gives the, and wait a minute, G of 1, so G of 1 is this, and G of 1 is e to the A, e to the B, e to the minus, oh, this is wrong. This is e to the minus A plus B. Okay. So finally, what this is saying is e to the A, e to the B is equal to e to the A plus B plus a half the commutator of A with B. Okay, so that's what needed to be proven. I'll put the proof of this on the web page, and I need to add an explanation of one step that I left out. So that's the result. This is, once again, the assumption is that the commutator of A with B commutes with A and B. When that's true, this works. Is Does anybody have a question or a comment? There is a more general formula for this, and the more general formula is a series that's associated with the names Baker and Hausdorff.
That's what I was going to ask, if that was like a special case of the Baker Campbell Hausdorff theorem?
Yeah,
Okay. I
yeah.
do have a question though, because you said that T is not time in the
Right.
beginning?
No, right, I just used T because I wanted to use dots as derivatives with respect to T.
T is just some continuous variable.
Just a T is just a parameter.
Okay, so what for the integration though,
Catch all.
Yeah.
it's just with respect to that parameter?
I do it accurately.
Yeah, it's
Okay,
just,
okay.
Oh, okay.
yeah, so
That-
d by
that way
dt,
it's
so
like
this
all
is
there.
the
It's not just in-
integral t 0 to 1
Can you see?
dt times ab. And so this is t squared over 2 evaluated at 1 and 0.
Yeah.
Okay, so that's called Glauber's identity, and it's useful in quantum optics because, of course, quantum optics involves annihilation and creation operators, and the commutator of an annihilation to creation operator is a complex number, and consequently, complex numbers commute with everything, and so this is generally true. It just occurs to me that there may or may not be an analogous relation for fermionic operators. There, of course, it's the anti-commutator that's a complex number. And that would be something amusing to look at. So if any of you want to look at such a thing and run with it, by all means, or find out if there's a Fermi, you might just be able to Google fermionic form of Glauber's identity, and you may find something. Okay, so the next step then is I want to apply this to the case of a classical current radiating, and this is related to Bremsstrahlung. Bremsstrahlung is when you have, say, an electron coming along, and it's accelerated because it passes near a positively charged nucleus, the nucleus being very heavy and having charge Ze. The electron becomes accelerated, and when it accelerates, it radiates photons off, like that. So to lowest order, one can think of this as a classical current. Namely, it's a current that flows like that, in which the charge accelerates and photons are radiated. So now, what is the S matrix? Remember, we have something called the S matrix, which is a time-ordered product of an exponential of e to the minus I, the interaction Hamiltonian, let us say the Hamiltonian density at x equal with x. So it's the interaction Hamiltonian density integrated over all of space-time, but then it's the time-ordered product. So this T does have to do with time. It's not just a convenience to avoid writing fractions. And the fields in here have free field time dependence. And And that's why we use this formulation. This formulation, by the way, I only learned recently, it's actually due to Dirac. And it's absolutely amazing how many aspects of physics are due to Dirac. It's amazing. So let's work in Coulomb gauge, and there the electromagnetic field just has vector components. And in fact, if I just look at a sub I of x and t, in fact, I'm just going to write that as a sub I of x, x being time and space, then this, of course, is an integral d cubed p over the square root of 2 pi cubed to p0. p0, since we're talking photons, it's just the length of the momentum vector. Of course, h bar and c, I said equal to 1. This is then pi of p and s, a of p and s, and e to the I, px, ei star of p and s, a dagger of p and s, e to the minus I, px. So that is the ith component of the electromagnetic field. Here we're talking Coulomb gauge. And what one does typically in quantum field theory when dealing with a gauge theory is one picks the gauge first and then quantizes. And here we're summing s equals to minus 1 to 1, let us say. In other words, there are two polarizations for each photon. And these EI of P and S, EJ of P and S, summed S equal to minus 1 plus 1 is delta IJ minus P hat I, P hat J. Let me just make sure that's right. Okay, so that's our electromagnetic field, and so this HI is just J dot A. After when one quantizes in the Coulomb gauge, the time component of the electromagnetic field becomes a dependent variable that is just given by an integral of the charge density, and I'm going to be ignoring the charge density here and just focusing on actual photons, and due to this current. Okay, so what do we do now to compute this thing? And the way I'm going to think about it is this way. We have e to the, I'm going to write JAI for j of xi dot a of xi dti. And so what we have here then is a time-ordered product I JA1 EVI JA2 EVI JA3 and so forth. That's our time-ordered product. And I'm suppressing, or let us call this integral d cubed xi. So the integral over x over space is essentially trivial. It's the time part that's tricky, because what we're talking about is a time-ordered e to the if I say h is that, then it's e. But let me put a minus sign there so I can have just plus signs. So this is an integral I j dot a d4 of x, but it's time ordered. And so this is a product of, if I write it again, it's e to the I j a n, e to the I j a n minus 1 dot dot dot, e to the I j a 3, e to the I j a 2, e to the I j a 1. So it's I'm just dividing the space-time into time slices, and everything is an integral over all of space, but the first time slice is here, second time slice, third time slice, n minus first, nth time slice. And of course, you're supposed to take the limit and go to infinity. Okay, so let's look first at e to the I JA2, e to the I JA1. Well, these are electromagnetic fields. The only operator is A and A dagger. The commutator of A and A dagger is a complex number, and so it commutes with A2 and with A1 and so forth. And so we can write this as e to the I JA2 plus IJA1 times e to the 1/2 JA2 JA1. So that's what we're going to use. And now the commutator, well, the commutator of J, I'll compute that in a moment, but let's just look at what we've got. We now have to do e to the I JA3, e to the I JA2, e to the I JA1. And so this is e to the I JA3, e to the I JA2 plus I JA1, e to the 1/2 commutator JA2 JA1. And now we'll apply Glauber's identity to this form, and what we get then is e to the I JA3 plus I JA2 plus I JA1. And now we have the commutator of this with that. This is already just a complex number, so we don't have to worry about it. And so we get plus 1/2 the commutator of JA3 with, I should say, IJA3. And these are I's. I left out the I's. And so this is the commutator of this with IJA2 plus IJA1. And then we also have e to the 1/2 IJA2 IJA1. Well, this is just the sum of all the IJAs. That's the nice term. And this one is the commutator, half the commutator of IJA2 with IJA1, and then the commutator, half the commutator of IJA3 with IJA2 and IJA1. So what we see building up here is, we can, if you want, I'll do another step, or I'll just say what the, do you want me to do one more step? Okay. So what we get then is that the product of e to the I JA K, say, is e to the I sum on K JAK times e to the minus a half, actually, of and what it is it's a sum on all k of JAK, and here we're summing K prime up to K of JAK prime. So in other words, we have 1 with 2, 1 with 3, 2 with 3, but we don't have 3 with 2 or 3 with 1. And so now we can change our notation and go back to what the actual expression is. And what we would have then is the time-ordered product of e to the I integral j dot a d fourth x. This will be e to the I j dot a d fourth x times simply a phase factor. And the phase factor will be e to the 1/2 integral, and so let's see. All right, let me write it the two ways. So it's, sorry, we don't need an extra thing, it's just a comma. So the commutator of those two as here, and I left out the I again, and the restriction here is that t prime is less than t, or x prime 0, x prime 0 is less than x 0. And now if we just look at that, suppose we relax that case, what would happen if we had this was obvious to me as just being a factor of 2 when I was in my office, and now I'm just wondering what do we actually say here. So we're saying here that we've got, let's say this is the t-axis, this is the t prime axis. So we integrate over these commutators for t greater than t prime. So we're integrating here. Now, what if we included one of these? Then, oh, but including one of those is like doing a minus sign, right? In other words, if we have a point here where t prime is greater than t, then it should come in with a minus sign, so. All right, let me just write it the way I'm sure it works. So this is e to the I integral j dot a d fourth x, and then a c number. And the c number is minus a half integral d fourth, or let us say d cubed x prime, integral dt minus infinity to plus infinity, integral dt prime minus infinity to t, and then the thing being integrated is, I factored out the i's. We have then ji of x, jk of x prime, commutator of ai of x with ak of x prime. And so that's the answer. Now this thing is an exponential of a linear combination of A and A dagger, and in fact, J is Hermitian, A is Hermitian, so this is a unitary operator. It's a unitary operator that's an exponential, that's linear in A and A dagger. That means you make a coherent state from the vacuum. So let me compute this thing, and I'll show you that this is actually just a phase factor. So the commutator there, let us just call it AI of x, aj of x prime. And I'm going to be using these expansions, this expansion of the Coulomb gauge electromagnetic field, the space component, so that the time component being a dependent operator. So this is an integral dqp prime, 2 pi cubed, square root of 2p0, 2p prime 0. And then what we have is the IPX. This px, by the way, is p vector dot x vector minus p0 x0. E to the I, ps, a of p, and s, plus e to the minus I, px, ei star of p and s, a dagger, p and s, big comma, e to the I, p prime, x prime, e to the ej of p prime, s prime, a of p prime, s prime, plus e to the minus I, p prime, x prime, e star j, p prime, s prime, a dagger, p prime, s prime. Okay, so we have to compute that commutator. And what we know is the canonical commutation relations here. Well, commutation relations for the electromagnetic field, creation and annihilation operators are so it's delta cubed of momentum and the Kronecker delta of the spin indices. And so what this does is it pops things out so that we just have an integral dqp over 2 pi cubed 2p0, and we then have e to the so a commutes with a, two a's commute, but a with a dagger gives us this delta function. And so that gives us e to the I p x minus x prime, ei of p and s, ej star of p and s. And then we have a dagger with a, so that'll give us minus e to the minus I p x minus x prime, ei star of p and s, ej of p and s. So that's what this commutator is. And what we now see is that it has the right complex structure to be just a phase factor, because this is a complex number minus the complex conjugate. Complex number minus complex conjugate is the imaginary part, or twice the imaginary part of the complex number. So this thing is imaginary. This is an imaginary number, and so this thing is a real number. J, the J's are real, this is all real. It's a real number times an imaginary number, so it's a phase. And so it's basically, it might be relevant in some cases, but I'm thinking of it as an irrelevant phase. We can go a little bit further here. In that we're summing over the S's, and so this thing is actually AI of X, a J of X prime is then an integral dq p to pi cubed to p0, and this sum over S, did I mention what it was before? Yeah, the sum over S, I left out a complex conjugate. The sum over S of the spin of a polarization vector times a complex conjugate of polarization vector is delta ij minus pi hat pj hat. And one of the reasons it has this form is that you need to make sure that if you dot p into this, you get 0. And so dotting p into that, we would have pi, say, delta ij minus pi hat pj hat. And so this thing gives us pj, and pi, p dotted into pi hat is, that's minus p dot j component of p hat, and that's just pj minus pj, which is 0. So in other words, this has the right structure to make sure that we preserve the Coulomb gauge condition, which is that the divergence of A should vanish. The divergence of A in momentum space is P dot A of P should vanish. And the part of A of P that's relevant here is the E. So we need P dot E. We need P vector dot E of P and S 0. So that's what is satisfied by these polarization vectors. If we were not at Coulomb gauge, if we didn't have any gauge condition on the vectors, we wouldn't have 2 of them, we'd have 3 of them. And then the sum over spin would give us just the Kronecker delta without this term. It's this term that enforces the Coulomb gauge condition. And so if we go back over here, what we've got here is e to the I p x minus x prime minus e to the minus I p x minus x prime times delta ij minus p hat I p hat k. So that's the commutator, and altogether then this thing is a phase, and the phase is e to the I phi, and phi then or I should say I phi, is then equal to minus a half times this integration. So it's minus a half times an integral d cubed x prime dt prime, and so this is minus infinity to t minus infinity plus infinity, and it's this structure here, aix aj x prime, and times jix jjx prime, and this is purely imaginary, so this is a phase. The important thing is e to the I a dot j, and if we just look at the a dot j part, then this is an integral d4 of x, let us say ji of x, ai of x, and so this is an integral d4 of x, jix, and of course this thing is dqp over the square root of 2 pi cubed, 2p0, e to the I px, e I of p and s, a of p and s, e to the plus e to the minus I px, e star I of p and s, a dagger of p and s. And now, what we can see happening here is that we've got an e to the I px, j of x, d4 of x. Those are the only places that x occurs. And so we can define j tilde, or let us call it just j of p, as an integral d4 of x, e to the I px, j of x. And so then this is, let me write it up here, a dot j, well, this is actually an integral of a dot j. So integral a dot j d4 of x then is an integral dqp over the square root of 2 pi cubed 2p0, and this then is just j of p, so it's there's no more exponential, it's j I of p, or if you want, j of p dot e of p and s, a of p and s, plus j of minus p dot e star of p and s, a dagger of p and s. So that's the formula. And so this is the argument of the coherent state. And so the Fourier component of, in other words, it's a coherent state that's a direct product of coherent states for each mode of the electromagnetic field, and the amplitude for each mode is j of p dot e of p and s. It's proportional to this. There are factors of 2 pi cubed and so forth, and then there's a continuum interpretation as you go from discrete quantization of the electromagnetic field to continuous mode quantization. In fact, it probably is nicer to do the change here. And if you did it here, then what you'd have would be basically a sum on K and S, because you always have this sum over S. And see, what I don't remember is what the factor is that takes you from continuum to discrete quantization. In any event, it's proportional to J of Ks dot E of Ks. And so those are that's what so in fact you don't sum over these at all. For each mode, the amplitude of each mode of the electromagnetic field is excited in a way that's proportional to that, and I would have to puzzle a bit to figure out what the corresponding factor takes you from the continuous representation of the electromagnetic field of the coherent states to the discrete representation. Okay, so any questions? There haven't been very many questions.
I'm just trying to take all the notes to write all of it down and read it
Well,
back.
it's on video though.
Yeah, but it's hard to see on the video.
Well, I will post the derivation of Glauber's identity on the class webpage, and I have already posted the Landau-Ginsburg stuff.
Yeah, I saw that.
Um,
Do you want me to shut the recorder off?
I guess so. I don't have a great deal more to say anyway.